Hi guys, this is the 8th video in the Math 9 ASI series. Today we're going to be going over derivatives, their properties, some things to look out for, and we're going to do a couple examples too. So let's just get right into it. So first off, the definition of the derivative. Let f be a differentiable function on an open interval I. The function f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. This is going to be our derivative of f. So remember, I think back in the first or second video or some of the earlier lectures for this class, we showed that this is actually just the slope formula, but we have this h, which is super, super close to 0 without actually being 0. Because if we wanted to plug in 0, we couldn't on the bottom, so we're going to take this limit instead here. So it's a slope between 2 points infinitely close to each other, so it basically gives us a tangent line at a single point, okay? And recall that a differentiable function on an open interval I is continuous, and this limit above exists for any x equals c in the interval I. So we have that every differentiable function is continuous, but not every continuous function is differentiable. That's important to remember. And also recall that the derivative is a function that gives us the slope of the tangent line of f of x at any point within our interval I. So for any c we plug in here, we're going to get the slope of the tangent line at x equals c. Okay. So next up, the tangent line. So we already know that f prime of x, or the derivative, gives us the value of the slope of the tangent line, right? So now if we wanted to find the actual equation of the tangent line, we can just use this. So let f be continuous on an open interval I and differentiable at c for some c and I. Then we have this equation, which is y is equal to L of x, which is just like a line, equals f prime of c times x minus c plus f of c. And this is going to give us a tangent line to the graph of f at c. That is the line through c, comma f of c, whose slope is a derivative of f at c. So notice that this is in the same form as point slope form. This is just point slope form where we're getting this slope value from our derivative. You can see here we have y minus y1 equals m times x minus x1. We have the same thing here. This is our m, this is our x minus x1, and this minus y1 has been added to the other side here, so this is our y1, okay? Now, if we want to check differentiability on an open interval, we need the limit to exist for any c over the interval, which is what this is basically saying here. And on a closed interval, we do the same process as an open interval, but we want to make sure that we check the endpoints. So if we're looking at the, we want to check the right-hand endpoint and the left-hand endpoint, right? So if we're on the far right side, then we want to check in terms of the left-hand limit, because there is no right-hand limit because we can't go past that endpoint. And if we're looking at a, or our left side of the function, then you have to take the right-hand limit because we don't have a left side, okay? And recall that this is very similar to the way we check continuity. We just check that if the limit exists for f of c. But this is a bit more of a complicated function, but the idea is still the same, right? So let's look at some examples and some non-examples of differentiability. So let's start off in the middle. This is an example of a differentiable function because we can draw along and we never have to pick up our pencil. So that tells us it's continuous. And there's no point where we're not differentiable, where that previous limit we looked at doesn't exist. But let's look at some examples here. So like this one, f of x is equal to the fifth root of 2 minus x. So at point 2, we see that we become basically a vertical line. So this vertical line, if you remember from the vertical line test, we know that this is kind of bad. The limit here is equal to 0. So what the slope is at x equals 2 is infinity, right? Because it's straight up and down. And a similar idea here is f of x is equal to x to the 2/3. we get this kind of cusp shape where we kind of come to like a single point down here at 0. And right here, we can't really say what the derivative is. I believe here it's going to be equal to negative infinity because we have 2 points converging and they're right at 0. We're in a weird situation where you can't really find the tangent line there because you have 2 different things coming in so just so strangely, right? So functions and the derivatives, what they represent. So f of x equals y represents the position of our point at time x. So if we're looking at our xy plot as maybe something in terms of time, x is our time, and then y would represent the position. F prime of x, these are a couple of different ways you can denote it. You can denote it with like a 1 in parentheses up here, or as y prime if we're calling it y. Dy over dx, this is saying the derivative of y in terms of x, or d over dx of f of x. And this is also known as the first derivative. This represents the slope of the tangent line of f of x at point x. Or if we're talking about if f of x is our position, then f prime of x gives us the velocity of f of x at time x. And similarly for our second derivative, we can denote the f double prime of x, where we have these 2 like apostrophes here, or you can say f with 2 in parentheses up here, or y double prime, or this is saying d over dx, or the derivative in terms of x of dy dx, or d squared y over dx squared, or the derivative of f prime of x, like this. There's a lot of different ways you can write this kind of stuff, and I want to make sure you guys, if you run into any of these, you won't be confused about it. I don't know why there's so many different notations, but you will end up running into all of these at some point. And what the second derivative represents is the slope of the tangent line at f prime of x at point x. So it's the slope of the tangent line of f prime of x, or in terms of f of x, this would be the acceleration of f of x at time x. Since acceleration is just the rate of change of velocity, right? And the relationships we have between them. So while f of x is increasing, f prime of x will be positive. And if f of x is decreasing, then f prime of x is negative. And the same relationship holds between higher derivatives too. So between f prime of x and f double prime of x, between f double prime of x and its derivative f triple prime of x, same thing. So if f prime of x is positive, or if f prime of x is increasing, then f double prime of x is positive, and so on and so forth, right? And I don't think we've talked about this in lecture yet, so I wouldn't worry too much about it. But the relationship between f of x and f double prime of x, while f of x is concave up, f double prime of x is positive, and while f of x is concave down, f double prime of x is negative. I'll show you what concave up and down means in the next slide when we look at the examples. So here we have our f of x is equal to x cubed, right? So it's just going to look something like this, where we're increasing and we slow down and increasing here at 0, and then we pick back up again afterwards. So the derivative here, f prime of x is equal to 3x squared, and it's going to look something like this, right? And notice that all throughout f of x, we're always increasing. There's never a point where we're decreasing. So we notice that f prime of x is always positive. And then for f double prime of x, we have f double prime of x is equal to 6x. So notice that while we're less than 0, we're negative. So let's look at that in terms of f double prime of x. We see that we're decreasing here all the way till 0. So that's why we're negative here. And after 0, f double prime of x is increasing, and so f double prime of x is positive, okay? And then in terms of f of x and f double prime of x, see how we're negative before 0? And here, this is what we would call concave down. If you think about it kind of like a cup, it would be like a cup facing downwards. Notice how the cup is facing downwards, so that's what we would call concave down. And here the cup is facing like upwards like this. after 0. So that's what we call concave up, and we see f double prime of x is positive after 0. Okay. So there's a couple of examples. Here we have some common derivatives. So this is some easy ways you can take the derivatives of some functions without having to go through that whole limit stuff. So in high school, my teacher introduced us to the power rule using this character, He-Man. He said that we now have the power because we know the power rule, which is kind of true. It's really super helpful for figuring out derivatives super fast, and I hope to pass that power on to you. So let's look at the power rule first. So if we have some x to the r, then the derivative of that is just equal to r times x to the r minus 1 power. So basically, we're just taking the r and we're multiplying it to the outside, and then the power just becomes 1 less than it was before. And this works for anything where r is not equal to 0. Since if r was 0, then x to the 0, we just have 1. And 1 is a constant, so looking at the constant rule, the derivative of any constant number is always 0, which is also pretty helpful to remember. And a couple other common derivatives. So sine of x is equal to cosine of x. Cosine of x is equal to negative sine of x. You'll notice that this is kind of cyclical, as we did, I think we showed in class. So if you take the derivative here, you get negative sine of x, and then derivative of negative sine of x is negative cosine of x, and then derivative of negative cosine of x is sine of x. So the cycle just keeps continuing as you take more derivatives. And here, the derivative of e to the x is always the same as just e to the x. Super easy, always the same thing no matter how many derivatives you take. And the derivative of natural log of x is just equal to 1 over x. Properties of derivatives. So these are a couple things to keep in mind when we're doing different kinds of derivative problems. So the sum and difference rule is if we're adding two things or subtracting two things, and we take the derivative of that whole function, then it's actually just the same thing as if we take the derivative of the first thing, and then we just add or subtract the derivative of the second thing. I believe there's a typo on this. I just noticed. This f of x here is supposed to be g of x, right? And we see that here is equal to f prime of x. This should be plus or minus g prime of x, okay? And then the constant multiple rule, we have that if we're taking the derivative of some f of x and it's being multiplied by a constant c, we can actually just pull the c out of the derivative altogether, take the derivative of the function, and then just multiply the c to that derivative afterwards, which is kind of nice when you have like a weird constant number with it and you don't really know what to do with it. You can just pull it out, ignore it, take the derivative, and then we can put it in afterwards. And so these are super, super helpful when we're finding derivatives, and it makes our lives way easier.